Hey guys, welcome to a new video in this computer vision tutorial. In this video here we're going to talk about edge detection. So first of all we're going to cover like what different kind of basic features are of edges in images, and then we're going to talk about like how we can find edges in images. And then at the end of the video here I'm going to show you like how we can actually like do some different kind of edge detection methods in OpenCV with C++. But first of all, remember to join the Discord server. I'll link it down in the description so you can chat with us in there. And we're talking about like different kind of stuff within computer vision, deep learning, artificial intelligence, and stuff like that. And also if you have some projects where you have some problems, you can go ask your questions in there. Or also if you just want to come chat with us. So let's jump into the first slide here, where first of all we're going to talk about what edges are. So edges, we can use edges in images here to like segment out objects or like some other different kind of important information in the images. So the edges is the analysis of discontinuities in images. So down here we have an example of edges that we're detecting in an image here. So we can see here that we're actually like segmentating out the most important information in the images here by having this edge detection here, where we're doing this analysis of discontinuities. So we can see that when we have an edge in an image, it is actually like a change in the intensity of the images, which we're going to cover and talk more about in this video here, throughout the video here, where we're going to talk about like how we can actually like find these discontinuities here and what they are, and also like what different kind of methods, like how they implement this way of like finding the different kind of edges that we have in images. So when we're talking about edge detection, we're actually like finding the different kind of like areas where the brightness changes abruptly. So when there's like a really large change in the brightness in some pixel values, then we can say that there's an edge between those. And we can actually like find those edges or like the changes in brightness by using derivatives. So we can find the changes by like using the derivatives. So we're actually like calculating the gradients and also the orientation of the gradients when we're trying to find edges in images. So over here to the right we can see that we'll have like these two circles here, and then the first one here is the black one here, and then we have the gray one, and then we want to find the edges here in the images. So we can see like here there's a change here in the brightness, so the brightness here changes abruptly. So we can say that we have an edge here, and to actually like find the edge here in the image we need to take the derivative of those values here, so we can actually like calculate the gradients, because edges have gradients and they also have an orientation. And this is what we can see down here with the arrows, which is actually like gradients and also the orientation. And they can be found by applying convolutional mask in both x and y direction, and some of the different kind of methods for actually like detecting edges in images that we're going to cover here is actually like just some filters that we're applying convolution to in both the x and the y direction. Then we're finding the edges in both of those directions, and then we can combine them together and actually like find all of the different kind of edges and the most important information in the images. So down here we have some different kind of edge profiles here that can like where we can say like this is an edge. So we can have like this step function here, so we can actually like have an edge here which just goes up here. So we just have a really fast change in the brightness or like in the intensity of the pixel values. And we also have like the edge profiles, which is real, and often they will be very noisy. So we won't have like this step signal here, like it will be more like it will be more noisy when we're actually like calculating the gradients here and finding different kind of edges in the images. But when we're taking a function and we're taking the first derivative of that function, we actually like find the maximum of that. So we can use that information to find actually like the maximum of the changes here when we're taking the first derivative. And when we're taking the second derivative, it will be 0 where we have an edge. So we can use this information here to actually like implement some different kind of methods and use that to detect edges in our image. So if we just talked about when we're taking the first derivative of the edges here, we're actually like looking at the image intensity function, and when we take the derivative of that, we will actually like find peaks or jumps in the images which will correspond to edges. So the first derivative here is the rate of change in two directions. So when we're looking at an image and we're looking like at the rate of change in two directions, then we will get that result by taking the first derivative to that image intensity function. And then we can the detecting edges here can be performed by locating like the pixel locations where the gradient is higher than its neighbor. So when we're implementing some of these different kind of methods here, we're actually like calculating the gradients, and then we're looking around at an area and seeing like if that gradient is changing, or if the gradient is higher than its neighbors. And then we just set up some threshold here where like if that gradient is higher than some threshold, then we're like dealing with an edge in our image. And as we can see here down here to the left, we can actually like see here that an edge is when there is a change in the intensity of the image here, which is also the same thing that we're doing when we're actually like calculating the gradient, as we can see over here to the right, where we have the formula here for the gradient and also for the orientation of the gradient. So we can see that we have the image intensity function up here, where we take the partial derivative with respect to the I direction here, and then over here to the right we just take the same intensity function here and take the partial derivative with respect to the other direction here, which is y in the x direction, and then we just sum that or like square that, and then we take the square root of that, and that will be the gradient of that image intensity function. And then we can also calculate the orientation of the gradient, so we can see like in what direction it was, which corresponds to the errors that was on the previous slide. So some of the different kind of methods here we have that is implementing the first derivative approach is the Roberts filter here, and the compass filter, the Sobel filtering, and thresholding. So these are different kind of methods to actually like that is actually like applying this first derivative approach that we just went over. And here to the right we can actually like see the original image here, where we have this Sudoku game here, and then when we take the Laplacian here over to the right, we can see that we get this nice and clean edges detected here, and the Laplacian is actually like the second derivative, which we're also going to cover here later in this video. And the Sobel x and y here is actually like this Sobel filtering over here to the left, and we're going to cover and go more in depth with some of these different kind of methods here in this video. But we can see here that when we're taking the first derivative, we're actually like doing it in first the x direction here, and then in the y direction, and then we can see that we get the lines here in both the x and the y direction, and then we can actually like combine those two together, and then we can get like the Sobel filter, which is applied in the x and y direction, and it'll look like kind of the same as the Laplacian up here, maybe a bit more blurry, but we can detect this like all of the same lines and edges that we do with some of the other different kind of methods. So now we're going to cover like what is convolution, because convolution is really important when we're talking about edge detection and when we want to find edges in images, because we actually like just have a kernel that we're applying to our image, and then we're just like sliding that window or that kernel over our image, and then calculating the gradients or with that filter that we're applying for one of the methods that we're using. So when we're using convolution here in images, we're just applying a filter or kernel on an image, and it is used in edge detection here, where we apply the convolutional mask in the x and y direction. So let's say here that we have like some kernel here that we just apply here on top of our input image, and then there's this output here from this convolution here, where we will like respond in an output here, which will be like tell us if there's like an edge here in the image, if there's a change in like the pixel intensities. And when we actually like want to calculate or like do convolution, we have this filter down here where we can actually like have this white and this gray here, where the gray value, where the white value is here is these three columns here with the value of 10. And then we use this convolution operator here, and then we want to apply this mask or this kernel filter here to this input image. And when we do this here, we actually like just apply it. So we just put this area here on top of the first area here, and then we actually like just calculate the values what will correspond to like when we're doing matrix multiplication here. And at the end here, when we're done convolving or like applying our convolutional mask in both the x and the y direction, then we'll have this resulting frame down here where we can see there where there is actual like edges in our images. So this is what convolution is and how we use that for actually like detecting edges in images. So another approach we can take is the Roberts edge detector, which is also like a first derivative edge detection. So it's really good for binding images because we have these two filters here, like these two really simple filters. So they're really fast to do the calculations, and we have these one value here, and we have the two zeros here, and then we have the -1, and then we just flip it over here, so we can actually like first take it in one of the directions, and then the other one is good for the other directions. So we can see here that when we're doing this Roberts here, it's really simple, so it's really good for binding images, and it's also really fast edge detector. But if we have like more complicated images, or like we don't have binary images, then this approach here would actually like cause a lot of noise to our image when we're using this Roberts edge detector. So this is really good for binding images, but if you have like just a normal image or like not a binary image, then you shouldn't probably use this Roberts edge detector here, because you'll just get too much noise on your image. So the other one here, and one of the most used one, is actually like the Sobel edge detection algorithm, or like because it uses the Sobel operator, and we're going to use that here as well when we're using the Laplacian operator. So we have this discrete differentiator operator here, which is actually like the Sobel operator, and it computes an approximation of the gradient of the image intensity function. So instead of calculating like the exact gradient of the image intensity function, then we just compute an approximation and use that instead for like speeding up the calculations and stuff like that. And also combines the Gaussian smoothing and differentiation, so we don't really like need to use like Gaussian before we're doing this Sobel edge detection algorithm. And we can see here that when we're using Sobel here, we're actually like doing it again in both the vertical and horizontal changes. So we look at those. So we apply this filter or these kernels here in both the X and the Y directions. And in this case here, we actually like have these two filters here, where this one here is good for the horizontal changes, and this over here is good for the vertical changes. So we're looking at the edges or like lines and like changes in the intensity in both the X direction and the Y direction. And then when we have found that, we can actually like combine it and find the resulting gradient here, so we can see like where is the changes in their intensity and where is the edges in our images. So this is just the exact same values as before, but instead of we're actually like taking the partial derivative of the image intensity function, then we're just using this approximation here with these filters here instead of actually like doing the calculations. So this is like a really good example, and this is just like when we're applying convolution here on our image intensity function. So another approach here we can take for edge detection is actually like doing thresholding. So if we have like for example a grayscale image here, we can actually just have a threshold, and we can say that if the pixel values is over some threshold, then it will just be it will just be 255, and if it is under the threshold, it will just be a 0, and then we will get like this binary image over here to the right, where we can see that we can detect all the different kind of lines here and also the other different kind of information here, because these are not white pixels over here in the left, like in the original image. So we can use edge detection or like thresholding here for edge detection, but this is like really like trial and error approach, and it only like applies to grayscale images over here. And there's also like a lot of different kind of information that we don't really need when we're doing like actual like edge detection applications. So over here to the right, we don't really need the information like around the table here. We just want the important information in here, and we want to detect the edges inside of this image here. So some of the other different kind of edge detection methods is actually like when we're going to use the second derivative instead of the first derivative. So the first derivative is just to find like peaks and changes and stuff like that. But when you're taking the second derivative to the image intensity function, we actually like get where there's a zeros. When we take the second derivative, that will actually like be the edges in our images. So some of the methods here that applies this second derivative here is the Laplacian of Gaussian, which just uses like the Sobel operator, but it takes the second derivative instead of the first derivative. And then one of the most used, or like probably most used edge detection algorithm is the Canny edge detection algorithm here, which we'll mainly focus on in the slides here. So we're going to talk about like what is the difference between the detectors and which one to use, and what like different kind of approaches for both. So the first one here is the edge detection here with the Laplace operator. So as I just mentioned, we have the second derivative here is 0. So when the second derivative here is 0, we actually like have an edge in our image. And the Laplacian operator here just like to take the derivative in both dimensions. So we take in the X and the Y dimension, and this will be the Laplacian operator here. So we have the partial derivative here of the function with respect to the X value here, and also for the Y value here, and then we sum them, and then we actually like get the Laplace of the image intensity function. And Laplacian is actually like when it's like implemented in OpenCV, it uses the Sobel operator internally. So over here to the right, we have the different kind of filters here that we're actually like applying when we use this Laplacian operator in OpenCV. And down here we can see that we actually like can detect the different kind of edges, and we only detect the most important edges in our image. But we can also see like we blur out the image, a bit. Like it's not really that sharp because we're taking derivatives, so it's not really that steep edges. So we will get like more smooth transition from over like the edges where there's changes in the intensity. They will get like it will be more smoothed out compared to like for example a Canny edge detector. So now we're going to talk about the most important one here, which is the Canny edge detector, and also the most used ones when we're talking about like edge detection and some of other different kind of algorithms that depends on detecting images before doing some other different kind of stuff. So it's known as the most optimal edge detection algorithm here, and it computes both the orientation and the location and the gradient. So it's both like calculating the orientation of the gradient and the gradient itself, and then also the location of like where is this gradient and orientation at. So we have some different kind of steps here when we're actually like applying the Canny method here. So first of all, we're going to filter out any noise with a Gaussian filter to make it easier to actually like detect the edges and images, and also reduce some of the noise that could like happen could occur in the image, so we can actually like get false positives when we're doing our edge detection. And then we want to find the intensity gradient here of the image, which is like the method here is similar to Sobel, which we already went over. And then we're using non-maximal suppression that is applied on the image here, which just removes the pixels that are not considered to be part of an edge. So when we're using this non-maximal suppression here, we're actually like taking a pixel here, and then we're looking at the pixels around it and sees like if this value is higher than some other different kind of pixels around it, just like as we already talked about, like when we're looking at the neighbors around a gradient that we're calculating. And then if that value is less than some value that is in the neighborhood, then we just discard that value and we only use one. So when we're using this Canny detector here, we actually like just get one value here for all of the different kind of edges. This is also the reason why we have this like sharp image here and like these sharp edges here compared to some of the other ones which will be like smooth out more of the edges in the image. And it also uses hysteresis here in the bottom here, where we're just using thresholds to filter out pixels. So we have like an upper threshold and a lower threshold, and then if the values are in between those, then we'll keep them, and if they're under the lowest threshold, then we'll discard it, and if it's over, then we know that this is certainly an edge, and we keep that as well. So down here we just have this hysteresis here. So if a pixel gradient is higher than the upper threshold, the pixel is accepted as an edge. And if the pixel gradient here value is below or like the lower threshold, then it's rejected. And if the pixel gradient here is between the two thresholds, then it will be accepted only if they're connected to a pixel that is above the upper threshold. So this is where we're going to look around at their neighbors when we're actually like detecting the edges in the image. So we can also apply edge detection here in OpenCV, and I'm going to show you like how we can actually like do it in code. So we have this original image over here to the left, and then we're applying edge detection here with the Canny edge detection algorithm, and then we can play around with the threshold here to like filter away some of the different kind of edges that we not really want to have in our image, because we only want to extract the most important information for some different kind of applications. And then down here we have the actual code, where first of all we're going to apply this Gaussian filter here, or like this Gaussian blur, so we can actually like smooth out and reduce some of the noise in the image. And then we can just call this function here, which is implemented in OpenCV, which is the Canny edge detector. And then we just give it the blurred image that we just blurred with the Gaussian blur. And then we specify the edges where we're going to store the actual edges that we're going to detect in the image. And then we set the lower threshold and the upper threshold as well for this hysteresis. So we actually like know when we should accept an edge in the image and when we should reject that edge in the image as well. So here we have an example of like when we're comparing Canny versus the Sobel operator. So the Sobel operator here is actually like when we're taking the first derivative in the y direction and in the x direction. So we can see that we are actually like smoothing out the changes or the edges more down here with the Sobel operator, because we're like trying to estimate or like approximate the actual like gradient and the edges in our image when we're taking the partial derivative. But over here with the Canny here, we can actually like see we get these sharp edges in the images, because we're actually like using non-maximal suppression, which we're not in the Sobel operator down here. So we're now into the Visual Studio here, and I'm going to show you like how we can actually like do this Canny edge detection here in OpenCV here in C++. So first of all, here we're just going to include the OpenCV library here that we're going to use, and then first of all we need to have these matrices here that we're going to actually like store the images, and also the grayscale image, the blur image, and the image where we actually like are detecting the edges in. And then we're going to set this kernel size here, which is actually like kernel size of the Laplacian operator that we're going to use. So this is like a 3x3 kernel that we're going to use convolution to actually like find the edges with the Laplacian operator on the images. And then we also have the depth here of the Laplacian operator, which is just like parameter that we need to specify. And then for the Canny edge detector that we're going to use, we're going to set the lower threshold here, which we're going to set equal to 0, and we also have a max threshold value here that we're going to set equal to 100. And then we're actually going to create a track bar, so we're actually like going to to tune and change these thresholds here while running the program, so we can see like how it affects the edge detection when we're playing around with these two thresholds, two threshold values here. So down here, if we start with the Laplacian detection here, then we can actually adjust. We're going to, in both examples here, we're going to use this Gaussian blur here. So we're first smoothing our image to reduce some of the noise that we have in it. And then we're using this grayscale, we give it the grayscale image here that we have. And then we sort in this blurred matrix or image here. And the size here that we're going to use for the Laplacian operator is a 3x3, for our Gaussian kernel. And then down here we have this Laplacian function here that's actually like just implemented in OpenCV. So we can just call this function here, and we give it the input image and the output image, and then we also have the depth of the destination image, and then we specify the size of the kernel, or like the size of the kernel of the Laplacian operator that we're going to use, as we went over in the slides. And then down here we can just convert back here to CV 8 unsigned. So we convert it and scale it absolute value here back, so we can actually like see what is going on in the image after we've done this Laplacian operator. So we go down here to the main function, and we're going to load in this Lena image here from this directory here that I have stored it in. And then first of all we're going to check if the image is empty, and if it is, we couldn't load it in, and we'll just throw out this error here and terminate our program. Or else we will convert our color here from the BGR here to a grayscale image. And then we can just have some name windows here that we're just going to use later on. We're going to actually like show the images here that we're actually going to find the edges in. And then down here for the Laplacian operator, if we start with the Laplacian operator, then we can actually just call this function here that we created. And then down here we can actually like see what is going on when we run the program. So when we run the program here, we can see that first of all we actually get up this original image here. And then we also get the grayscale image that we grayscale after we have loaded in the original image here. And then after that, we're actually like blurring out the image to get like these like more smoothed out edges in the image that we can actually like just then detect. And then over here we have this Laplacian edge detection algorithm that is implemented here, where we're looking in the X direction and the Y direction. And this is what we can see here where we're actually like applying the internally the Sobel operator, where we can see that we're smoothing out the edges more here because we're taking like the second derivative, and we're using the partial derivatives here and approximation of those. So now I'll show you like how we can use this Laplacian edge detector here. And if we go up here for the Canny edge detector, which is a bit more like exciting and also more used out in the real world. So up here we can go up to this Canny threshold function here that we've created, and then as I just showed you in the slides where we had that example with OpenCV and how we can actually like do Canny threshold, or like get Canny threshold value here. So first of all we're going to blur out the image here again with this Gaussian blur, and then down here we can just call this Canny function here, which is implemented in OpenCV. We give it the input image, the output image, and then we specify the lower threshold here and the upper threshold. And then we're actually like going to create a track bar so we can like tune and like lower and make these different kind of threshold values here higher, and then see what is happening in the image with the edges when we're actually like changing these threshold values here. So we have this function now here, and if we go down here to the main function, then first of all here we're actually like going to create this track bar there, so we can slide the different kind of like threshold values. So I'll just comment this Laplacian edge detecting out here, and then we're going to create this track bar where we have this minimum threshold value that we're going to specify, and that we can like actually like slide, so we change the values. And then we just specify the different kind of parameters here with the lower threshold value, and we give that as a reference. And then we also have the max lower threshold value here, so the maximum value that we can slide this lower threshold value up to. And then we need to specify this callback function that we just created up here, which is the Canny threshold function. And this is the same as up here. And then when we want to actually like do Canny edge detection here, we need to call this function here Canny threshold again, and we just passed in these two zeros here because we have this int up here, and then we have this void pointer up here to actually like be able to create the track bar in OpenCV here with C++. So if we run this program here, we're actually like going to create this image here and do the different kind of operations, and then at the end here we will actually like get the edge detection in our image here and the track bar that we get up here on the top. So first of all we have our original image here, we grayscale it, and then we blur it out to like reduce some of the noise, and then over here we're actually like applying the Canny edge detection algorithm, and then we have this this track bar up here, and we can actually like change the minimum threshold value here, and we can see that when the minimum threshold value here is 0, we're actually like detecting all of the edges that we have in our image here. So we get like all of the details here on the head here and in the and like on the hair here and also in the background. So we're actually like extracting all the edges that we actually like have in our image when we have this minimum threshold value of 0. So if we change this and slide it a bit up here, and we can see that now we have a threshold value of 50, then we can see that we don't really have that many edges here in the background. So we remove some of the less important information. So the most important information is actually like the face here and some of the details here in the head. And we can even slide this further up here, and we can see that we just get less and less information like the higher the minimum threshold value here is, because then it will be closer to the maximum threshold value, which is 100 in this example here. So if we slide it up to 100 here, we can actually like see that we're only extracting the most important information. We don't really get that many details here in the head as in the start. And also we have this clear face here where we can see like the nose here, the mouth, and also the eyes. And we don't really have that many edges detected in the background. So even when only like when we have these edges here, we're only extracting the most important information in the images, and then we can use that further on to actually like do some different kind of like object segmentation and stuff like that with the eyes or the mouth or some other different kind of stuff like that. So this is like how we can apply Canny edge detection algorithm here in OpenCV with C++. So we've been over like how edge detection actually like works, and also like what edge detection is, and also like what is an edge and what describes an edge in the image. And then we went over some of the different kind of methods and how we can apply edge detection with the first derivative, with the Sobel operator and the robbers and stuff like that for binary images. And then we also went over the second derivative with the Laplacian operator and also this Canny edge detection algorithm here. As I already mentioned, like it's the most used ones, and it has really good performance, and we get these nice and sharp edges here because we're using non-maximal suppression that we already went over. So thank you guys for watching this video here, and remember to hit the subscribe button and bell notification under the video here, and also like this video here if you like the content and you want more in the future. I really appreciate your support. It helps me and the YouTube channel out in a massive way. I'm currently just doing a deep learning tutorial with neural networks, where we're talking about like convolutional neural networks, how convolutional neural network work, and also then we're going to creating convolutional neural networks and also artificial neural networks from scratch, training it on some data set, and then we're actually like going over the training process epoch per epoch, and then we're going to evaluate the result and do new predictions on data that the neural network hasn't seen or trained on before. So that's a really nice tutorial, and we'll also combine it with this computer vision tutorial here, so we can see like how computer vision and deep learning with neural networks work together. So if you're interested in that tutorial, I'll link to it up here, or else I'll see you in the next video, guys. Bye for now.